Good to see some of your faces again. For those of you who are at the afternoon welcome session of the Learning for Action cohort, my name is Seth Collins. I'm the director of the Learning for Action program, and I will be hosting a lot of these guest talks that we'll be having with our esteemed speakers throughout the arc of the course. I know this is a talk that we open up to the public. This is our keynote talk for the Sea Turtles cohort, which is our 33rd cohort of the Learning for Action program. And so for those of you who are joining and are not part of the program, just wanted to welcome you all as well. And simply to give you a quick overview of this program, this Learning for Action cohort is a group of 210 folks from, I believe now we're at 29 different countries from all over the world who've come into this program to find ways to more effectively deploy their own skills that they have towards working on climate change. Folks in this program have skill sets that across the broad breadth of professional skills. We have students, we have senior leaders, we have mid-career professionals, we have people who are retired and are looking to just continue to contribute and learn. And so we're always just so excited to have everyone here. If that's something you're interested in, you can learn more about it on our website, join an open house. Zach, really excited to have you here today as our keynote speaker. So folks, I'll just give a quick brief of Zach's bio. Zach Labe is a climate scientist at an organization called Climate Central. His research specifically focuses on the intersection of climate risk, climate impacts, future scenarios, extreme events, early warning predictions, and data science methods like AI and ML, machine learning. In addition to that work, he is very passionate about improving science communications through accessible data visualizations. And we use, if you've started taking some of the classes for this week, you may have already come across some of Zach's visualizations that we use in our modules. Before his time at Climate Central, he was a research physical scientist at NOAA in their Geophysical Fluid Dynamics Laboratory. He has a PhD from the Department of Earth System Science at the University of California, Irvine. And his particular focus that he's always had is looking at the links between Arctic climate change and specifically sea ice loss and its influence on large-scale atmospheric circulation and extreme weather. There's a lot more you can learn about Zach. He has a very great and active social media following as a climate scientist. He's got a website, zachlabe.com, that I can put in the chat so folks can go and check it out as well. I definitely recommend following him and sort of tracking some of his graphics. I've found them to be useful in some of our own trainings that we've run at different times. But with that, Zach, I'm going to hand it over to you for the beginning of our keynote talk. Just a reminder to folks, those of you who are Learning for Action Fellows, you have a link to a Slido in your cohort channel, and we're going to use that for question and answer. We are going to prioritize questions from our fellows. If you are not joining as a Learning for Action Fellow, please still feel welcome to ask questions in the chat, and we can use the chat as a space for dialogue anyways. But just an invitation to the Learning for Action Fellows. We will prioritize your questions here, and that's the best place to enter them. And I see a number of you have already. Okay, Zach, over to you.
All right. Well, thanks for the great introduction. And hi, everyone. I'm really excited to be joining with the kickoff of your cohort. Hopefully you can see my slides. Let me know if there's any issues as we go forward. So today I'm going to be talking a lot about a wide variety of different things, going into the origins of climate science, to science communication, to why I think we need more science communication. And I'm going to be particularly talking about my journey, thinking about how we can better visualize climate change to communicate to the public. And so you may have noticed this sort of squiggly line at the bottom of my title slide. Well, that squiggly line is one of the most, famous graphs we have for understanding anthropogenic climate change. And so, there's going to be tons and tons of visuals in this presentation, but I thought I'd start with this classic, which is showing changes in carbon dioxide for almost the last 1 million years. So on the left-hand side is that 800,000 years ago, and on the right-hand side is where we are today. So of course, there's ups and downs, things like ice ages and such, but today's spike is of course unprecedented. So I like to ground us again to keep always reminding us, what the data is that shows the evidence for what's happening today. And so again, about me, I think, I love being a scientist. So my research is really trying to better understand climate change, both in the past, present, and future. I think a lot about climate impacts, particularly regional climate change, and really what I'm trying to do now I'm at Climate Central as a climate scientist is how do we connect climate change impacts to people? How do we understand if influences to communities and the impacts associated with those, and how do we reach others? So I think I can really am fortunate to be able to wear both hats of sort of scientific research and communication. And so what we do, what is Climate Central? So Climate Central is a nonpartisan, non-advocacy nonprofit, and our focus is on scientific research around climate science and also communicating it. So a big part of what we do is how do we break down the complexities of climate science, again, to people to make it more understandable and accessible. And one thing we work a lot is on a topic called climate attribution. So essentially what that means is how do we understand day-to-day changes actually in weather, and how do we attribute that to climate change? So you can go to our website and play with this tool. Basically, what this tool is every single day you can go on and take a look at a map around the world, and it will tell you how much temperatures in every area around the world, how much climate change is contributing to those temperatures. So here's today's map. I'm on the East Coast, located in Pennsylvania, and we are at this climate shift index of 5, meaning that is the maximum on the scale, and that climate change is contributed to change in the likelihood of at least 5 times more likely the really excessive heat and humidity we've been feeling across the eastern coast of the United States. And I'm really lucky that my research has been, I get super excited about a wide range of topics in weather and climate. So I always have a hard time giving an elevator pitch of what I actually research. But really, the crux of it is trying to break down what is climate change versus weather. And often I call that the noise. And then how do I communicate that through visualizations? So I want to sort of break down, what a day-to-day looks like from climate science researchers. So we work with lots of numbers. So I sit behind a computer all day working with climate models and observational data. And this is basically, the data looks like. This is just a so small image of millions and millions and millions of numbers of a climate model output. So obviously we can't look at these numbers and understand really what's going on. So of course we need to visualize it. But the Earth's system is so complex because we have so many things going on, which makes it, challenging to understand how it's going to change going forward into the future. Because guiding it all is incoming radiation from our sun. So here's a visualization of that sort of seasonality and changes in radiation. So again, you're seeing seasonal differences. You can also kind of see the reflection from snow in the northern hemisphere. So looking at the reflectivity of the Earth's surface in that image. We also, need to monitor the transfer of heat. So here is sort of an image that we can look at that, thinking of through temperature. So here's again showing this seasonality to temperature. So in the purples and reds are warmer temperatures around the tropics. Around the northern and southern hemisphere towards the polar regions, you can see more of some blues and greens. Those are colder temperatures. You can see how it oscillates through the seasons. The cold temperatures come down during the winter time. We also have, this huge storage of heat that's not coming just from the land, but it's through the ocean. The ocean is a huge heat capacitor. And so you're seeing here changes in the oscillations of the ocean temperatures over time. And then we have moisture to deal with. Moisture is one big complexity in weather forecasts and climate science. So here's showing what a visualization looks like for moisture around the world. So in the whites and purples, that's showing higher moisture content in the atmosphere. And then you can see these little plumes that come out of the tropics into the northern hemisphere. So bringing moisture northward. Those are actually called atmospheric rivers. So if any of you live along the West Coast, like in California, you're very used to dealing with these types of plumes of atmospheric rivers that bring heavy precipitation during the winter time. So all of these features and phenomena we need to try to model as climate scientists to understand climate change impacts. And so we do all that, we put all that together through mathematics, and then we essentially get output like this. So this is a globe, it's spinning around through time, and you're seeing the change in Earth's temperature it'll go all the way out to 2100. And as it slowly goes through time and you see the Earth is warming, there's a couple other interesting features I want you to notice. One is there's this huge red blob forming at the top of the globe. So that's the Arctic. Arctic's warming super fast. We'll talk about that more in a minute. But another key feature that I think it's always important to remember is that look at the land versus the ocean. And what you can see is that the land areas are getting much more red. So the land where we live is warming much faster than the oceans. So that, of course, means heightened impacts for people and communities. And it's always important to keep in mind that the land is warming faster than the global average. And so I want to break down through all of this through how I think about communication. So again, I think about it through visualization. So I want to go through this conceptually. And a key point you just saw on that previous globe was that this big red blob over the Arctic. So the Arctic's warming more than 3 times faster than the global average. And this is actually a very well-known statistic that we can trace back all the way to the most early climate models from the 1980s. So I realize this isn't quite as pretty of an image, but this is really groundbreaking science. Actually, he won the Nobel Prize for this. I'll show in a minute. And what you're looking at is actually a map from a very early climate model in the 1980. Anywhere in shaded, it means more warming. So you can see that even in the earliest climate models, we knew that the Arctic would warm faster than the rest of the planet due to more carbon dioxide. And so if I were to show a graph of this, in a traditional science jargon type graph, it might look something like this, where it's a line graph. You can see the white line is the Arctic. It's warming much faster, much steeper slope than the land and the ocean, which are in the other colors. But there's a lot of jargon here. This is not an easy graph that I can just show, to non-scientific audiences. So often when I start my presentations, I actually start with this image. And so there's intentionally no labels on this image because I want your eyes to really take a look at the patterns. What do your eyes perceive? So I'll give you another clue that each of these circles is a map. It's a map of the Arctic. So you're looking downward on the North Pole. The bottom land in each little map is showing northern Canada and Greenland. And then the top of the map is sort of Asia and Europe. So then after, I have you take a look at this image, I'll start adding some labels. So what are we looking at here? So we're taking a look at Arctic temperatures in their departures by year. In climate science, we use this word called anomaly. Anomaly just means how does the temperature compare to average? So I'll add some more labels here. So now you can see what we're looking at. We're looking at maps of the temperature anomalies from 1979 at the top all the way to present at the bottom, 2024. Anywhere in red is warmer than average. Anywhere in blue is colder than average. So now you can see these patterns that your eye was perceiving, that there's generally a lot more red in recent years than at the top in past years. But you can see that these colors are not uniform. Some areas are blue one year, then red next year, and there's some variability, we'll call it regionally. And that's this idea that there is climate change and there is weather. And we need to try, as climate scientists, try to distinguish between the two. And again, just to remind yourself, this scientific term for all of this is called polar amplification, this really accelerated warming at the top of our planet. And I also want to just remind everyone, climate science. I think it's always important to reflect on the history of climate science. Even though it seems, climate change has only been in the news, I don't know, last couple decades or so, the history of climate science actually dates all the way back to the early 1820s. And a scientist, mathematician named Fourier, who you may have heard in some of your math classes, actually first posed the question, and of Earth's temperature, basically trying to compute the planet Earth's distance from the sun and what would the temperature be based on that distance. And he found that Earth is a lot warmer than we should be based on purely the distance we are from the sun. So that there must be something else that's keeping our planet warm. So then, sort of the next historical event in climate science was a climate scientist. Her name was Eunice Foote, who really created this amazing experiment that helped us understand, okay, given our distance from the sun, why are we warmer? And basically, what she did is she filled up tubes, glasses of different gases and placed them outside and recorded the temperature over time as they were heated. So you had a gas of just hydrogen, a gas of carbonic acid, so getting at carbon dioxide. And she found that the one filled with the carbon dioxide was a lot warmer than the other gas tubes, giving a clue that maybe this gas, carbon dioxide, could be a reason why Earth is warmer than we would be expected, so that the carbon dioxide is trapping heat in our atmosphere. And so, even then, in the early 1900s, there were actually newspaper articles that started talking about, hey, maybe the burning of fossil fuels, at the time coal, it could lead to a warming of our planet. So this is actual newspaper article from Australia in 1912 that identified that the burning of coal could warm our planet. Going forward, again, in this sort of historical overview, then in the 1930s, we actually started getting our first reconstructions of Earth's temperature, noticing that, hey, we are actually warming. So a scientist named Guy Callender actually was able to assemble some weather station data from around the world and plot these little graphs on the right-hand side that showed that Earth's temperature during this early 20th century was actually starting to warm, and maybe it was due to carbon dioxide from the burning of fossil fuels. So then, going forward to the mid 20th century, this is when climate models started first becoming a thing. So, a scientist named Suki Manabe, who worked at NOAA Geophysical Fluid Dynamics Laboratory, was the first to really develop a climate model like that early black and white map I showed. And this is really, an amazing understanding of combining all of these complexities in the Earth system through math to really predict climate change. So here's showing an evaluation of how well those early projections were actually compared to reality. So if you look on the right-hand side at the upper right, that's showing output from the model from the 1980s. So just focus on the colors, the oranges and yellows. And then on the bottom, that's showing what actually happened in the real world. So you can see that if you match the oranges and the orientation of the yellows, this climate model, this primitive climate model from the 1980s, was already able to make pretty good predictions of climate change. And so what are these climate models? What are they today? So we've seen that the history of climate science, it's been around for hundreds of years. We've had climate models from over 50 years that we can now validate and showing that they're doing pretty well. So what's the state of the art today? And the state of the art today is really quite complex climate models. Climate models actually are some of the largest producers of data for any science in the entire world. Because you have to think, as a climate, we're trying to model not just the atmosphere, but we also measure the depths of the ocean. We also do things like the depths of the soil. We're predicting going forward to the future. We also have climate models that go back thousands of years. So you have all of these different dimensions which produce petabytes and petabytes of data. So we can only run them on supercomputers. And all of this is essentially done by mathematics. Really, we're just trying to understand the motion of the atmosphere. Don't worry about the equation here at all. It's just showing that these are the types of differential equations we use to model climate science. And it's how we do this, it's through computer code. So what we do is we write code for these mathematical equations that represent motion in the atmosphere. And that is how we have climate change projections. That's how we have an idea of what 2100 might look like. So what's my role? What's my day-to-day and why I think science communication can be an even bigger part of a scientist's job. So I'm going to run through an example of one project, how long the project took, and contrast that with science communication. So what I do is I run on these supercomputers. So here's what these supercomputers actually look like, and you can compare that to your sort of home laptop. So you have a warehouse that's essentially the size of a computer that we run the climate models. So for several months, here's an example project I did. For several months, I'm working on gathering data. So I'm looking at climate models, I'm looking at observations, I'm identifying statistical and data science types approaches that take, several months. Then I sort of perform, very initial types of experiments to really understand the data, exploratory data analysis. I then, once I have a better understanding of the data, then I start performing more experiments. I run additional experiments. I write code for analyzing it, utilizing statistics or things like machine learning, again, taking several months. And again, that's through code and lots of data to look at. And then, of course, I need to understand the data. So I need to create visualizations. Eventually, once the scientific hypothesis and outcome is more visible, I then have to write a research papers through, through interpreting my results. So I make visuals of what's happening. And that can take quite a substantial amount of time. And then I have the peer review process, which can take anywhere on a good day from 6 months to several years just to publish a paper on this topic. And so here's what that might look like eventually. So the challenge here is, okay, so I've done all this scientific analysis. In many cases, for the scientific community, that was kind of the stopping point. They do all this, research on climate change topic that would impact millions of people around the world, and then the paper would be published and it would disappear, online, and maybe no one would ever read it. So what think we need to be doing more of is how do we communicate that, and how do we communicate that effectively in plain language? And a challenge with all of the scientific process, I mean, there's good reason that the scientific process takes, up to multiple years for one project. But a challenge is the climate change is happening really quickly. So here's a visualization of temperatures during 2023 and 2024. And what you're looking at, the thin lines are showing all global temperatures for other years. And then the yellow is these last recent years. So what you can see is during this same amount of time that I was working on this one specific research topic, globally, the climate was rapidly changing. We were observing record warmth that was way outside of our understanding, our records. It even this term, this headline came out from a scientist that was that year was gobsmackingly bananas. September 2023 was an outrageously warm year, and how do we keep tracking this data that's changing so quickly while we also have this long scientific process? How do we balance these two to understand risk and communicate that to people? And so for my method of all of this is data visualization. And it took me a long time to really think of it as a form of storytelling. When you go to science communication workshops, especially about climate change, they always tell you, focus on human-driven stories, not data. Don't throw numbers, don't throw facts or graphs at people. So for a long time, I thought, oh no, my method is doing exactly that. It's throwing lots of visuals at people. But I've come to realize that by thinking about how do we tell a story through the data and making our graphs more accessible, breaking down complex jargon and all the scientific nuances, that it can actually be a really powerful way of communicating climate change in real time. And I think I'm always reminded of this contrast of, we are data scientists as climate scientists, but stop thinking like such a scientist. So use your skills in working with data and contrast that to, think creatively. And I think there are so many powerful examples of how do you take data and communicate that in a creative ways. And this is one of my favorite examples. So it's an artist named Gio Pelto who took real world data and turned it into watercolor paints. So on the left-hand side, if you actually look closely, there are little data points. It's showing things like the decline of glaciers of ice, or in the red, the flames there, that's showing changes in ocean temperatures. So combining data with art to tell the climate change story. So okay, let's go through a process of a specific graph. So here's probably the second most famous climate graph after that one of carbon dioxide. So what it is it's showing the global temperature by year. So the white line is showing the temperature for every year. The red line is just trying to smooth that out because you have that year-to-year fluctuations from weather. And it's showing data all the way from 1880 on the left through present day on the right. Reflecting on this graph, there's tons of jargon. It's a difficult graph to communicate that to broad audiences. So let's try to think this in creative ways. What are some ways we can take the same data and communicate that to people? Okay, so let's say I were to open up my computer code. I would take the data for global temperature for multiple data sets. So the legend here you're seeing is just we have multiple different observations data sets that we use to monitor Earth's temperature. So each line is one of those data sets. So if I just took the data and put it in the code and didn't change anything, it would look something like this. Again, not pretty, not easy to communicate that to people outside the scientific community. Okay, so one climate scientist, the name of Dr. Ed Hawkins, decided to take that data and throw a different spin to it. And this was through, it's now called the climate spiral. So again, same data as that line graph, but now visualizing it in a completely different way. So what you're looking at is Earth's temperature changing by year, but you can see it's growing as this outward spiral. So it's, perceiving this and visualizing this is such a completely different way than the line graph. And it ended up being an incredibly powerful tool for communicating this to wide variety of different audiences. It was so effective that this climate spiral was actually featured in the opening ceremony of the Summer Rio Olympics. Before this happened, I wouldn't ever have guessed or believed if someone had told me that a climate science graph would be featured in such a powerful venue. Again, showing the power of visualizing data through telling a story. So, if you're interested, there's this wonderful piece that was written by Ed Hawkins on sort of, thinking back, reflecting on this journey of how the climate spiral was just a way of thinking creatively to communicate complex information. And so it's not just me or it's not just the climate spiral that says, there are good and bad ways to visualize data. There is an entire, scientific research area that thinks about how do we perceive graphics? How do we perceive information? So I love this example that is done from this study. So you're looking at 6 different maps. It's showing the change in Earth's temperature in every single map. So every map has the same data. The only thing that's changed here is the color of the data. So you can see, there's reds, and then on the right-hand side, some sort of, different colors. So then they took these 6 maps, the same data, just changing the color, and they asked people a survey, a series of questions. So I'll just go through a couple examples. So this question was, how severe would you estimate the global temperature increase with respect to the appeal of color? Which map would you estimate, climate change being most severe? So in this case, the first map, the brighter reds, was selected for this one. Then the next question was, which color scheme appeals to you to be the most intuitive one for climate science? So in this case, they picked a different map, the one below that. So the brighter reds suggested to people that climate change was more severe, but actually the colors below that with the more subtle red was more intuitive. And then another question that I think is interesting that they asked is, which map would you choose to affect policymakers to take more action on climate change? In that case, this question led to that first map with the brighter reds, maybe suggesting more extreme conditions. But I think the takeaway here from real scientific research in cognitive psychology suggests that color can really influence visualizing and how we perceive things like climate change. And this is so important because, as we all know, the climate change is happening in real time. So we need to constantly be communicating that, like in the Arctic, which is seeing even more rapid changes. So we need to continue doing the scientific research, but also monitor these changes as they are happening. And it's really another, way we should be communicating that. So something that I've liked to monitor and communicate is changes in the amount of sea ice in the Arctic, which has always been one of the classic indicators of climate change is ice loss. And typically what you're looking at here is a graph of the amount of sea ice. So you can see there's sort of this peak and then there's this bottom. What that is it's showing the seasonality of sea ice. So sea ice grows during the winter, it then shrinks during the warmer summer. That sort of seasonal cycle is normal. The problem is the Arctic's warming, so you're getting a lot more melt than normal during the summer. So it's melting more than it can grow. But traditionally, there were only 2 times a year that news articles and media outlets would report on changes in Arctic sea ice, and that would be at the maximum and minimum. So twice a year, winter, summer. But by monitoring what's happening day to day in the Arctic, there's a lot of extreme events happening and it's affecting people. People live within the Arctic. And the Arctic has far reaching effects. It's basically the refrigerator of our planet. So here's an example in 2016, which was a very extreme year in the Arctic. So that's the red line. So you can see that there's lots of bumps in that red line, lots of dips, and all of these were associated with extreme events. There was one point we saw temperatures rise well above freezing at the North Pole during the fall. So by monitoring the data in real time and tracking it and communicating it to people, we can have a better understanding of the types of impacts we are facing on our planet. And this is an opportunity to share stories. And again, my journey of thinking about the power of visualizing data has changed over time. And one graph that really changed my perspective on it was one from quite a few years ago. This was in 2018, back when I was using Twitter more regularly. And I created this graph showing changes in Arctic temperature. That's the one on the left. And you can see that there's this little red line that spikes. That was 2018. So essentially, on the right-hand side, you can see a map of this big red blob. This was this heat wave that hit the North Pole during the middle of winter. Temperatures rose to almost the freezing point. Um, so it was quite an extreme event. So I sent out this graph showing what was happening on social media, and it took off. It really went viral. And to me, it was shocking because when I look at this graph and reflect on it, it's pretty complex. It's pretty jargonful. I don't think it's very accessible. But people and audiences are really looking for communicators, trusted messengers, and scientists to communicate in real time what's happening to our planet. And so I think it's just an example of that there is such a big longing for actually scientific expertise and trusted communicators to talk about what's happening. And it's all about starting conversations. Here's just another example of an extreme event. This time it was in Antarctica. There was a huge loss of sea ice during their winter season. And it started conversations with people, what's happening in the Antarctic? Why is this happening? And connecting it to climate change. So you might say, okay, well, these are all, data examples. What about impacts? So here's an example within the Arctic of another extreme event. So this time was also 2018, where basically there was no sea ice in the Bering Sea. So this is a region of the northern Pacific Ocean that's between Alaska and Russia. And there are many communities, indigenous communities in Alaska that live along the Bering Sea, and they rely on sea ice for many different sources of their livelihoods. They rely on it for infrastructure, they rely on it for transportation. And this was a winter that the ice actually melted in the Bering Sea. I spoke with one community that all they have to transport supplies to that community is an airstrip that's on a piece of sea ice that's been there for every single year in their history. In 2018, this winter, there was no ice and it was just purely open water. So there was no way to transport supplies to this community. So even though you may think of this Arctic being this really far and remote place, it's affecting people. And I think by monitoring the data and communicating it, we can talk about what's happening with others. And I think another frame of reference I like to think about is the weather forecasts. So my original roots, I grew up loving the weather and I thought I was going to become a weather forecaster. I grew up in a small town where I actually didn't know anything about climate change until I went to college, where then my career switched a little bit. But we think about the weather. We have a weather forecast. We see weather forecasts every single day and we're constantly talking about it. But do we talk about it like climate change? So the way I've always thought about, how should we think about climate information is, could we do something similar like weather forecasts? Could we create, websites and dashboards where we can go on and find what is today's data for sea ice, today's data for land ice, for glaciers, for the Earth's temperature? So I started creating a website where you could go and find all of this up-to-date information and monitor it as it was actually changing, sort of going around, the scientific process where it might take 2 years for us to understand that sea ice during the winter of 2018, where on my website, you can go and track it in real time. And I originally started with it just a very simple graph showing what's, greenhouse gases, what's current levels of carbon dioxide, current levels of methane, how that's changing. I then, based on feedback, so certainly when you post and share things on social media, people don't hesitate to share if they like it, or especially if they don't like it. So I'm constantly always adjusting my figures based on people's suggestions and constructive critiques. So then started adding some more variables to a dashboard that people can monitor. Also monitor this for changes in the Arctic. So again, I'm flying through these graphics, but just showing, examples of what these data look like. You can find all of this on my website. And it's not just for the Arctic, it's not just for, things like greenhouse gases, but you can go and look for indicators of things like sea level rise or things like the loss of land ice. So here's showing a loss of land ice. Land ice is going down. The previous graph was going up because loss of land ice leads to rising ocean waters. So all of this data that, you may or may not hear about periodically through the year from the media, you can go and track yourself. And here's just another example. This is an indicator showing what's happened to the world's glaciers, which are declining. Again, we can monitor information like this in real time. And I also like to really break down, how did I create these visualizations? So to me, it's not enough just to put the graph there, but we also need to increase trust and transparency around the data that, showing that climate science has been around for hundreds of years. Here's how we get the data, here's how we process the data. So I also create blogs to try to break down, where does this data come from? How do we use it as climate scientists? So I, some once a month, I create visualizations and then go into a sort of a deep dive of, what's the science behind the visual. So here's an example showing little maps of changes in temperature during the summer season. And there's lots, I could spend a whole day talking about just the science behind this visualization and what you're seeing for this graph. But just showing examples of different types of visualizations you can use for storytelling. And of course, pointing back to the data, to me, one of the strongest things we can do to increase, climate communication and make it more robust is to be more transparent. Cite your sources remains to me like the best piece of advice, I think, for combating misinformation. So in every social media post that I share a visualization, I also include the link to show here's where the data is. My ultimate goal, I realize many people don't care at all about where the data is coming from and don't want to look at it or dive into the technical details. And that's okay. But there are some people who are actually interested, who want to be brought along into the scientific journey. To me, it's about breaking down the barriers of science and the ivory tower, and how do we make this more transparent and accessible for others and bring them in to the scientific process, because ultimately added trust and transparency, it improves science. I think it makes for better open science, open data. And that leads to innovation. That leads to innovation in terms of improving our scientific understanding, but also innovation in terms of things like climate change solutions, climate change adaptation, and mitigation practices. I realize most of my talk, I haven't focused on climate solutions. And to me, that's because my expertise and my training is really in this physical science, the changes that are happening. But my colleagues that, sit next door to me, there are hundreds of them that their expertise is solutions. But ultimately, by making the data more transparent and increasing trust, that leads to better innovation for those solutions where people are working on all of those important topics. And I think again, ultimately, it's a reminder of think creatively, take the data and think creatively about it to communicate what's happening. This is another visualization you might have seen before called the climate stripes. So again, this is taking that same global temperature data that you saw for that line graph that I said was too jargony, and then turned into the spiral that was going outward. Now it's turned into these stripes where there's no numbers, no labels, and again, color telling the story. So the blue stripes are colder years, the red stripes are warmer years. On the left is older, going back in the past to like 1900. On the right is present. So it's reflecting, of course, climate change, that the earth is warming. And just another way to spark conversations and talk about people. Funny enough, Ed Hawkins also created the climate stripes, and it was interesting to see how people were receptive to the climate stripes. So you found that non-technical audiences love the stripes. I've seen examples of stripes on t-shirts, coffee mugs, dresses, even cars, soccer jerseys. So it was it's all over the place. But scientists were kind of nagging, like, how can you create a graph without labels and units? So I like this kind of solution that he created, that you could add on some labels and, showing the years at the bottom. And I think it goes back to, reminding the scientists to stop thinking like such a scientist when we need to communicate this information. And I really encourage you as you go through your fellowship to remind yourself that we need everybody at the table to think about climate change. We need not just scientists, but we need people to educate. We need innovators to think about climate change solutions, renewable energy. What are some new ways to think about adaptation and mitigation? Our infrastructure is going to need radically change to adapt to extreme events and natural hazards that are changing. And all of this needs to be communicated. And I think reflecting on my time, doing science plus communication is, to me, there is no right answer to communication. For me, it's about doing what you're comfortable with and following your passion for communicating climate change. And I just want to coming to a close here to get to questions, and just want to say that my career would not have been possible without federal research. We're at a time where our federal institutions across all sciences, but especially in climate science and climate change, is being, for lack of a better word, attacked. And admittedly, I was at NOAA earlier this year and affected by the probationary terminations. So I, have been directly impacted by what has happened by Doge and such, and can talk about that in another day. But I just want to highlight that all of this science, these advances we have, an understanding of why climate change is a problem, all goes back to federal research dollars, which makes all of this data free and publicly available, and supports all of the communication, in training for students, for professionals. And so I think it's just important to really highlight the importance of federal research behind everything that we do to understand climate change. And then I'll just bring us to an end with reflecting on, again, this is the picture of where we are for climate change. And I will end here, and I'm happy to take questions. Thank you.
No, thank you so much, Zach. If you want to maybe stop sharing your screen so we can all come back together. Yeah, awesome. Well, I've got a few questions that we have from our fellows in our Q&A, and I have a few questions I put together as well, and I'll kind of be the synthesizer for all of us. And so I hope I've been trying to take all the questions that have come in and put them together in ways. So let's see if we do a good job of this and get the most of these questions into that folks have. So starting with let's start big picture. Given where we are right now, we've got record temperatures, extreme events. Would you say that climate science communication has been a success or a failure? And what do you think has most helped or hindered that effort?
Yeah, good question. So I think so. It's going to depend on who you talk to. I'm going to say it's a success. It could, of course, be better, especially reflecting on, politically what's happening. It seems like we have a long way to go, but there are a lot of successes. I think climate scientists in particular, and climate science as a whole, has been one of the most effectively communicated sciences, because the field of climate change has been politicized from the very get-go. So misinformation, is not new to climate, change and climate science. And there's been so much progress. We've learned so much on how to effectively communicate these topics and make progress in making change. There are many examples too that show that there have been successes in increasing renewable energy. We are certainly avoiding the worst case scenarios that it looked like we were headed if I gave this presentation 15 years ago. So we are making progress. I think when we reflect on surveys, there's great work by social scientists on asking surveys about understanding of climate science and communicating that. And we see that across the United States and all political spectrums and locations that people know what climate change is and its source. So to me, there have been many successes and advances over the last couple decades.
No, thank you. Um, so when I was doing my master's degree at Oxford, I don't know if you know of Miles Allen, a climate scientist, but was one of my professors, and I remember him making this comment that all the best climate scientists or are all the best climate models aren't in the public domain because they're held by financial institutions or insurance companies. And so I was curious, first of all, how true is that? Because it's something that I think is interesting when we talk about the public data that we have. And someone was curious about what organizations are using this data and why. So I was wondering if you could just go into that a little bit. How is this data, being used in other places besides this sort of public communication stream and research that you're talking about?
Yeah, yeah. So there's sort of two parts to this. So the one is free and open data. That's coming from the federal science, so that all your climate models that you're seeing, the data for the future, directly output it. Basically, everything I showed here today is free and publicly accessible. So you can dive in if you would like to the millions of lines of code of a climate model and see exactly what decisions and math is behind it all. And you can access all that data yourself. But so that's one side of things that's free and accessible. The other side of things gets into more the specific natural hazards and impacts. So getting into things like risk modeling, which a lot of more and more startups and companies are pursuing. So trying to provide local scale risk information, like how will my risk of flooding change going forward into the future, or how will changes in energy demand for, very small scales. So companies are starting to create their sort of own risk models behind these types of hazards. And a lot of them are proprietary. So we don't know what is really behind the hood unless you're at that company. So a challenge is sort of when we get to the applied side of things, which are the impacts that affect people, where insurance companies, civil engineers, they need this type of information for planning. A lot of that is often coming from sort of behind the paywall. So I think it's this challenge from the origin of the science to then these individual risk models, and how do we verify that this risk information is valid. I think are very open questions we're now trying to grapple with going forward into the future.
Staying on that thread of sort of that localization thing, that context that you were saying, one of the questions that we got from one of the fellows that was upvoted a few times was how to best work with on the state and the local level to contextualize the impacts of climate change to drive action. And maybe what are some examples that you've seen? Maybe these are ways that your own work has sort of taken off in certain contexts, and I'm sure you've gotten feedback on it. So yeah, curious what are some examples of that you could share?
Yeah, to me, this is the most exciting work that I do, is working with state and local officials. So I'll give a couple examples of like successful collaborations. One thing is these are challenging. So they're super fun, but they're difficult because you have to speak different languages. I come at it from my own science language, but someone who's a community decision maker is coming at it from their own language. So half the challenge of this is meeting in the middle. So one successful collaboration that we've been doing when I was at NOAA, it was working with the American Society of Civil Engineers. So basically, all of the building codes for infrastructure for the entire United States do not take into account a changing climate. They've only started to think about climate change more recently. And so this big collaboration started between NOAA scientists and all of these civil engineers to think about, okay, how can we come together to improve infrastructure building codes to plan for the hazards of the future? We're already seeing this. This summer, there were examples here in New York City where the drawbridge would not shut because it was so hot that the bridge expanded and it would not close. So there's so many types of infrastructure related things. So we had all of these meetings where we came together to try to work with, civil engineers, work with communities and building officials to understand what do they need from us? What do they need from the scientists? And a lot of what we were finding is the data that we were producing with the climate models wasn't the right data that they need. One, it was produced in a format that they couldn't access. So that, of course, that's a huge problem. But another problem is they need really local information. So one uh, industry we were working with was freight railroads. So they need really fine spatial detail to understand things like heat stress on railroads. And our climate models were producing very coarse data, meaning that the data was not, relevant for something small like a railroad. So it was working to understand how can we make the data, one, more accessible in a better format that they're used to working with, and two, what are some variables that they need? What are some type of metrics we can create? And ultimately, it led to a successful and fruitful collaborations that were now starting to incorporate climate change into building codes to think about how flooding might change in the future, how heat might change in the future. So to me, there are so many different avenues in combining these types of sectors, especially with local communities, that there is a lot of work left to do, and they are excited. I constantly am hearing communities again all across the country. They want this data and they want to understand it.
How do we make sure this data is accessible all over the world and useful all over the world? I think some of the examples we've talked about have been sort of focused on North America, and we've got folks from kind of all across the global South as well here. And to kind of, I think, bring in a few other questions I saw, are there ways that that data is being used well or misused in certain contexts? And how do you navigate that?
Yeah, yeah. This is a huge challenge. So, like I said in the beginning, climate models produce some of the largest volume of data of like any science you can find. So, how in the world can we transfer this type of data in our infrastructure? And so, this is a huge challenge. I don't have a perfect answer for this, but it's again, it's about having conversations with researchers in the global south of how can we provide the data that they can access it. I'll give a quick example in the Arctic where I work a lot. So in the Arctic, we're trying to understand all these changes in sea ice and how it's impacting coastal communities, indigenous communities. And so we're, sending them images of the sea ice so that they can, understand how it's changing. But they can't access the images because they have either no internet at all, no wireless infrastructure, or it's just a very limited bandwidth. And we couldn't even transfer some of our simplest, smallest images through their data infrastructure. So it became a huge challenge. And so now there's organizations in Alaska that actually can be sort of this intermediate group that we can send the data to this group and then they can go and visit the communities to have one-on-one conversations in person to discuss this. So I think it's really about having conversations, bringing these locations around the world into the conversation, into the planning stage. So don't wait until the data's already done, the science is already done before bringing them into the conversation. Bring them in from the very beginning, co-production of knowledge.
No, thank you. Um, well, I think we'll do two more. Uh, we're at a time where it feels like there's a strong pushback against climate action, especially in the global north right now. You've been on a long journey of encountering, I can imagine, many climate skeptics. And there's both the world of climate skepticism and the world of climate denialism, and those are different things, and they're pushed in different ways. But I'm noticing more and more conversations I'm having where folks who were maybe denialists a while back are now saying something a little bit differently or noticing things or talking about the flooding that's been happening over and over in their backyards and things like that. Um, so when you do encounter skeptics, as many of our fellows might in one of the assignments that they do, um, what have you found to be the most effective tools to respond or share with them in order to have a constructive discussion?
Yeah, I think my go-to is don't say climate change. So, as an example, I give a lot of public talks. I was at a rural central Pennsylvania talk a couple weeks ago, And basically, I just stood up there and showed, examples of how the climate is changing in their region, how the weather is changing it, tying it to agriculture, showing that plants are blooming earlier, and temperatures are warming, and never saying the word climate change. And I can see nods in the audience say, yeah, yeah, my crops are not growing at the same cycle they were before, or you know we're seeing changes, this whiplash from drought conditions to very heavy rainfall going back and forth, which is also affecting my, crops and farms. And then the clues start, you can see almost the crank being turned that, okay, maybe something is changing. And so you can then tie into going back to the sort of the foundations of the science. To me, it's really about, breaking down, making all of this transparent. I realize again, there are many answers to this question. And I encourage people to follow, again, their passion for how they like to go about this. But for me, it's about the transparency in the science. I'm not trying to hide anything. You can go find the code for how I make these graphics available. Here's the steps I made for making the data. Here's what's happening. Here's what's happening in your local community and connecting all these dots.
Last question. You're faced daily with data that communicates a rapidly worsening climate. What gives you hope in the face of all of that? How do you navigate that?
Yeah, good question. To me, it's about when I started this communication journey. So it's never really, up until recently, now I'm at Climate Central, it's never was a part of my job. It's a long discussion, but in science, your career, you're not really rewarded or supported for communicating it. You're supposed to do research and write papers. But I thought, oh, I'll give it a try. I like communicating. Let me see, how it goes. And I'm still shocked, even after doing this for 5, 10 years of posting these visuals online, of like the supportive comments from around the world that I receive. And people are looking for this type of information. They just don't always know where to get it or who to get it from, these finding a trusted messenger. So I can find so many examples of where people are like, wow, they've never seen a graph of changes in carbon dioxide or changes in global temperature. I post these same visuals every day, and every day someone will say, I never saw that before. Wow, that's really eye-opening. And to me, that gives me hope. Another thing is lots of people reach out to me and they want to know more about the graphic. For example, they want to look at the sea ice graphic. They want the data so that they can have their students practice making graphs or practice statistics. And to me, that's so exciting that people are getting so interested and invested into the science and they want to be part along the journey. They just don't know where to find the information, given there's just so much thrown at people on social media. So we need more communication, especially now.
I think that's an apt final closing piece, a headstone to this talk. So thank you, Zach. I really appreciate you having your time and bringing your energy to this conversation. It was it's so great to just go along that arc with you, and I think it really contextualizes a lot of what's happening in the modules for the fellows right now. So thank you, thanks everyone for being here. The 108 folks who have been here with us. I know we didn't get to every question, but we tried to get to as many of those as we can. If you do more of these questions that you have, hold on to them. We have next week, we'll have a deep dive on climate science, and one of our instructors, Anders, will be there, and he'll be able to answer a lot of these questions that you have as well. And you can follow Zach on his social media platforms. I put it on different social media platforms. I put his website down in the chat as well, so you can go and find that because I knew there were some questions for that. See lots of thanks and praise coming in through the chat, so that's awesome to see too. Um, for the Learning for Action Fellows, just a simple thank you. Hope you're doing well. I know this has been a hot start. We'll be moving into the next couple, and pun not intended there, but pun partially intended. And we're continuing with climate science over the next week. We'll have another climate scientist and IPCC author, Chip Fletcher, who will be with us next Wednesday. Dr. Chip Fletcher has been doing guest talks for Learning for Action since the very beginning of our first cohort. And it's a really, really strong and powerful talk. So I really encourage you to be there for that one. It's going to be in the evening Pacific time, not in the morning, because Chip is based in Hawaii and we don't want to make him wake up at 4 a.m. to give a talk. And so that'll be a bit of a different time. And I would definitely say catch the recording if you don't see if you're able to join it live. Um, again, Zach, thank you. Everyone, thank you so much for being here. Wishing you a great rest of your day, however long that may be. And keep working on your assignment ones. That's our big focus for the rest of the week, your visualization exercise. Maybe you can bring some data visualizations into it, even though this is your own visioning process. But I think there's some nice alignment between those two things too. So Zach, once again, thank you so much. And everyone else, have a great rest of your day, however long that may be.
Thank you.